Hello, everyone. Welcome back. I hope that you all have a great reading week. And I don't know. I'll be honest. I'm surprised that there are so many people. I'm surprised there are so many people here today. I hear you have a 2080 assignment due today, tomorrow. Oh, you have 2 assignments tomorrow. I'm sorry. Really tried, but I'm. Stuff because not a very the assignments. Any specific your own your any other section, please email definitely be early next week, but it should be soon. Today I was wrap OCCF, the Orthodox Canonical Class Form. Last particular, the idea of this idea, we went through the process of adding destructors to our classes, and I published some solutions to train class so that we could all of the other class instances that we own. I want to quickly revisit today, really just by looking at them again. So take a look at the destructors, take a look at how virtual the hierarchy being called, that sort of thing. But the bulk of the time that I spent today is looking at reference parameters, copy constructors, and the assignment operator. So in a sense that we need to have 4 specific things on our class, 4 specific things on our class: the null constructor, destructor, copy constructor, and assignment operator. Those are the 4 things that we should have in a class. This is OCCF compliant class. What I'm going to do is just finish that up so that we can add copy constructors and assignment operators. And as a result of that, we have to talk about reference parameters. Before we get to that, I want to know if there's any questions about the assignments while we're all together here. Yeah. Constant strings. The way that you would do that is I'm going to go to item here. You can do something like this that we called here in subtypes with passing the type that we wanted. So in item here we got this type. Then in potion down here, we're passing up to the constructor the string, the type that we're using. The other way is to declare like static attributes to your class. So a static string, and then having an uppercase name, and then using the class reference to get access to the string. Okay. So that might be because string is like a non-primitive type. It's an actual object type. Yeah. What I would do in this case is probably just up from the subclass to the superclass. Yeah, in the constructor. But just to make sure that you understand, you're doing something like this. The string type. type. You're doing something like that. Trying to is equal to pre-arrow, something like that. Yeah, because this is not a primitive type, we can't unfortunately do stuff like that. We can't initialize a primitive type thing. The way that you do this, and I gotta be honest, I haven't done this for a long time, and I might be making a mistake in what I'm saying, so take that for what it's worth. But the way that I believe we're supposed to initialize this is we have an item.cpp here. We would say something like this. Oh gosh. Semicolon. Okay, so we declare the type and make properties here that's a constant, and item.cpp say type equal to like I believe that's what we do, but please don't quote me on that. Okay? Okay. My advice would be to do what I'm doing here, just pass it up to the constructor way. Pass it up to the constructor that would accept it. Yeah, does that make sense? Okay. Is that any better? I don't know. They're like 30 seconds behind. You could just unplug them. Thanks for being the voice of these disembodied people, I guess. There. Hopefully that's better. I don't have the lapel mic on anymore. It's coming through loud and clear here, so. Any other questions? Yeah? So in your superclass, if you really need to access the values from the superclass and the subclasses, you should either make them protected or you should add accessors for those variables in the superclass definition itself. So it's a static variable that's attached to a class will be attached. There will be one instance of that variable for the entire set of instances of that type of class. So it does behave the same way as a Java one. So like if you do like a static variable and then plus plus on the static variable, it's the same one for all instances of the class, yes. So for primitive types, you can just assign a value to them in the header. So you could set it to be 0. So like if you have a counter or something like that, you can set it to be 0. To declare it, yeah. So you'd say something like static int, something like that. Yeah. You'd have to refer to it by the class names type. So when you are referring to it, you'd have to say item : count plus plus, something like that. How is it going? How is the assignment actually going? I have very little sense because nobody comes to my office hours. Nobody comes to visit me during office hours. And I mean, there's lots of posts on the forum. And I can't tell, I legit can't tell the difference between we have no idea what we're doing and we're just going to keep doing that. It's that? Okay, yeah. And I can't tell the difference between that and we know exactly what we're doing. We just don't need any help. Ah, oh, good. So I should expect the view count to be in the thousands for that, is what you're saying. The view count should be in the thousands. Okay, yeah. Oh, gosh. It's this one. Okay, that should be louder. I haven't changed any settings, so I'm really surprised that But thank you for being the disembodied voice of people that aren't here. Any other questions about the assignment? Yeah. So generic is meaning that we want you to create one queue class or one list class, and then you should be able to put any type of the objects that you've created into that queue class. You did what, sorry? You used a template. So we're not going to talk about templates in this course. You're welcome to use them, but we're not going to talk about templates in this course. Templates would be the way that you would do the same thing that we did in Java with generics, like having those angle brackets. Yeah. The idea that we're looking for with the generic queue or generic list here is the same approach that I described, where you've got like that super type list item, and then you're extending classes off of that to say, these are the types that you should have or should be allowed to be put into this list. Okay? It's not forbidden, no. Yes. I shouldn't say it that way. Yes, yes, yes. Yeah. So when I say one queue, I mean to say you should make one queue class. You should make 2 instances of that queue, because you need to have one queue for your customers and one queue for the events that you've been creating as part of the whole system. But you'll have one queue class. Yeah. And how's the 2080 assignment going? Is that going okay? Okay. Yes. In the Pokemon example, one was a priority queue and one was a regular one, but in this case, they're both priority queues, because the customer queue that you have, the customers have priority. Some customers have higher priority than other customers in this example. In the simple Pokemon example, it was just, they're all the same priority. Yeah. Okay, all right, okay. Related to the assignment, this isn't expected, but related to the assignment, I want to tell you a little bit about Valgrind. Valgrind. I'm going to say Valgrind. Valgrind, you may have seen before in Comp 2160. You may have seen this before in Comp 2160. If you haven't, that's totally okay, because I'm going to tell you what you need to know right now. If you have seen it in Comp 2160, this might be old news, but that's okay. It's nice to get a refresher on this stuff sometimes. Valgrind is a piece of software that is described as an error detector. And it can help you find errors in code that you've written, in C and C++ code that you've written, that's related to things like memory usage, so leaks of memory, so not calling destructors and all the dynamic memory allocation that you've done. It can also do things like error detection on threads. We're not doing threads in this course. You won't do threads until you're in operating systems, but this is a tool that you can use to help you with bugs that are related to multi-threaded code. Caching issues, so on your CPU you've got cache, it can help you with that, and branch prediction. So this is related to kind of like assembly language programming. And if you take Comp 3370, that's where you'll see this stuff. Valgrind is a piece of software that's installed on Aviary. This is a command line tool that's installed on Aviary. You can install it on Linux systems. I don't know if it's installed as part of Xcode. It might be installed as part of Xcode, but this is definitely available on Aviary. Similar to LLDB, you have to add -G to add symbols, debugging symbols to your program. So when you run your program, it has debugging symbols, or when you compile your program, it has debugging symbols. If you are using Clang++, which I'm guessing most of you are, is anybody using G++? Okay, if you're using G++, you don't have to change the way that you're doing the -G, you just use -G. If you're using Clang++, you have to do -G dwarf 4. So this is all one thing. This is all, they're all together. There's no spaces here. This was an interesting thing for me to find out. And this is a complete digression, but debugging symbols that are attached to your program are attached to your program in a specific format that's called dwarf. The program format, when you compile a program on a Linux system, the binary format is called ELF. Yeah, it's ELF. ELF is the name of the binary format for programs on Linux and Unix systems, and then dwarf is the debugging symbols for that. It's a joke, haha. Okay, good. I would like to try running Valgrind to give you a sense of what you can do with it and what the output looks like and how you can use it on your own programs. So I'm going to switch over here to VS Code. And what I've done to this program is I've already made the change to -G to add that dwarf 4. Again, if you're using Clang++, you need to do this. If you're using G++, you don't. So when I compile this, it's going to be compiled with the right debug symbols. And what I want to do right now is run Valgrind on some of the programs that we have written, so the test item and the test trainer programs. To run Valgrind, what you do is you pass the name of the program that you want it to run. So you say Valgrind, and I'm going to run it on test item. You have to have that ./ in front of it. I think this is also true on Aviary as much as it is on my own system. When you run Valgrind, it will run your program for you. And what it will do is monitor memory usage. It's going to keep track of all the dynamic memory allocations that you've tried to make, and then verify that you have released all of the memory allocations that you have made. So this is true for C and C++. This works on both of those platforms. What you can see about this test item program is that at exit, 0 bytes were in use. So that means that all of the allocations that we made in that program were released at the end of that program. They were not being used anymore. This is what you want to see as an output. This means that you do not have a memory leak in your program. If we run this on Valgrind test trainer, it's going to run it, and this is what we don't want to see. This is the output that we don't want to see. This is telling us that there is a memory leak in our program. When the program exited, there were still 80 bytes that were in use, so dynamic memory allocation for 80 bytes. But by default, it doesn't tell us anything about what that memory is. It just says, hey, there was still something in use. There's this nice little bit of, hey, run it with this option leak check full to see details of where that leaked memory is. So let's do that. And I've typed this in before. I'm going to run it. And what this now tells us is it tells us where, so right here, where that leak happens. So where the memory was allocated. Of course, it was never released. That's why it's a leak. But it can tell us where it was allocated in the first place. So if I open up testtrainer.cpp here, and I go to line 15, what this is telling us is that it was that new operator that caused the dynamic memory to be allocated. And that's happening on line 15 of the main function in testtrainer.cpp. So here, we allocated this memory for Pika2, and we never called delete on that object. So at the bottom of this, we never actually tried to delete that. So to fix a problem like that, I would say delete, call the destructor myself, deallocate that memory so that it's not being used anymore. Make that again, and then run Valgrind again. And now we don't have any memory that's being leaked by our program anymore. So it can tell us what memory is being leaked, how much is being leaked, and it can tell us where to look to find out where it has been allocated. But that's all the help it can give us. At that point, we have to figure out where we need to deallocate that memory. Good, 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 good. Okay. Would this help with finding seg faults? No. LLDB is the right place to look for seg faults. And well, here. Okay, so that's bad. We're saying release this thing and then release it immediately again. And I'm going to make it, and I'm going to run it, and it'll seg fault. So my seg fault looks a little different than yours, but it's still saying seg fault, sig V. I'm going to run this LLDB. You might see the same thing on Aviary. I remember seeing this last term. If you see that, you can safely ignore it. LLDB itself can be scripted with Python. We're not doing any of that. We're not doing anything like that. All this is saying is that it can't find the Python stuff. So you can safely ignore that. Run it, and then you get your seg fault. And then the best thing that I would suggest you do here is backtrace. This will tell you how you got into the state. So I typed in BT there for backtrace. This will tell you where you have seg faulted and how you got into that state of seg faulting. And then once you are in this state, you can use the commands up and down to navigate through the stack frames that got you into that state. So here, when we go up in the stack frames, we're in the destructor for Pokemon because we're trying to call the destructor again on something that's already been destructed. But once you're in this state of moving up the stack frames, you can start asking questions about the state of variables. So you can use P as a command to print things and then to put variable names after that to get values. So Valgrind is not the tool to help you with seg faults, but LLDB is the tool to help you with seg faults. Yeah, yeah. Okay, all right, cool. So I'm going to get out of LLDB there, and I'm going to switch back to my slides. And well, like I said, I want to kind of go through really quickly those destructors. I just want to remind us, because it's been weeks now. It feels like it's been weeks since we saw any of this stuff. So I want to quickly take a look at the destructors and when they get called and what the structure of that looks like, and then move on to some more interesting stuff. So Orthodox Canonical Class Form, OCCF, this is a description that says classes that have these 4 methods in C++ meet what Orthodox Canonical Class Form is. If these methods are not written by you, they will be generated by the C++ language itself. They just get created for you on your behalf. The 4 things that you must have are a null or a null-ary constructor. You have to have a destructor, and this is what we visited last time we were here. A copy constructor, which you may have done in Java, probably not, but you may have done this idea. I'm sure you've seen the words deep copy and shallow copy before, and this is related to that idea. And then an assignment operator. So if you've done any Python programming before with classes, you may know that you can overload operators in Python by implementing methods on a class, and you can do the same thing in C++. We can overload what operators are doing. To get to each of these, we're going to be talking about reference parameters. We're going to be looking at reference parameters as part of that. But first of all, why do we care? Why do we care about OCCF? OCCF is just this idea that we've got these 4 methods, or if we don't write them, they get generated for us. But why do we care about that? Why do you care about OCCF? Why do you care about OCCF? Why do you care about OCCF? Why care about OCCF? This is an open-ended question. Why do you care about OCCF? I like these answers. Yes, okay, good. I'm told it's important. What does it do? I couldn't tell you. Because that's a really good reason. It is a genuinely good reason in this case. I need it to pass 2150. Yeah, yes, yeah. Well, I mean, not really. You don't need it to pass 2150, but if you want to get like full score on something, yeah, definitely. Consistency in C++ classes. So that's actually a good answer. That's a really good answer, to have some consistency across C++ classes. One of the things that we had in Java was this. One of the things that we had in Java was class object. And everything derives from class object. You never say it, but everything has a superclass of object in Java. There is no class object in C++. The root of this hierarchy here that I've created with item, it's item. There's nothing above that. There is nothing that sits on top of that. There is no superclass for item. In Java, there's class object, and class object has no superclass, but you don't write it. Everything that you write ultimately extends class object. Because we use it often when coding. When you're doing C++, yes. This is not true for Java. Because it comes for free with the language, you don't have to do any of this stuff in Java, but in C++ you do. To make code reliable by removing defaults. I like that one too. So yes, OCCF is like you get these things for free as part of your class definition. You get a null constructor. But the null constructor just sets the defaults of whatever like primitive types have for the instance variables that you've got. So it's going to be stuff like 0. To get a degree, I guess so. It'll probably be in the midterm. Probably yes. I have no idea what that's supposed to mean. Oh, that's just the first thing you find when you search Google for OCCF. OK. That's a good point. When you search Google for OCCF, you're probably not going to find much. OCCF comes from an idea from a long time ago, from a really long time ago. In C++ and modern C++, this is more likely to be called the rule of 3 or the rule of 5. And the rule of 3 and the rule of 5 are more related to the idea that if you're doing something, so like in Java, we have 2 methods on objects. One of them is called hash code, and the other one's called equals. And 2 objects that have the same hash code must be equal to each other. This is kind of like a contract that's stated in the object class for Java. The rule of 3 and the rule of 5 and OCCF, the kind of like forebearer of these things, are this similar idea. If you have one of them, you kind of have to implement the other one. In Java, if you implement hash code, you definitely got to do equals. And if you do equals, you should probably do hash code as well to make sure that you're getting the same thing as output from there. It's a conspiracy. I've heard some really interesting conspiracies. One conspiracy that I heard, and this is maybe a little bit too close to home, but one conspiracy that I heard was that the program changes that we were making were coming from Brian Mark, the Dean of Science. And I have no idea why anybody would think that. I don't know. I don't have any idea why anybody would think that. Brian, I mean, he cares about us. He cares about all of us. He cares about us because we're in the Faculty of Science. But I have no idea why anyone would think that, that Brian would have anything to do with that. To keep programming standard, which in turn makes it readable, okay, yeah. The computer might generate a function and that does not do what you would like the method to do. Yes, that's true. So it likewise related to the primitive types. So you can celebrate again on Orthodox Christmas. Okay, if you celebrate Christmas the first time, then yes, you have an option to celebrate it again. Need to know about functions that are generated by the compiler if not provided. Allows for hierarchy control. Yes, because it might mess something up at some point. Yes. It could mess something up. If you make an assumption or if the compiler is making an assumption on your behalf about the values that something should have and you don't set them explicitly, it might mess something up. Yeah. Okay, good. Thank you for that. My answers are, I don't know, LOL, but really I've answered this already. It's a lot more about having some kind of consistent expectations across class implementations. Classes in C++ don't have this root type that is object that says these are the basic things that you can expect all objects to do. Having something like that, even though it's not really enforced in any way, gives us the ability to at least expect classes to have certain things implemented on our behalf. All right, so destructors. Let's just quickly run through destructors again, and then we'll move on to something new. So destructor is a public method on a class. Java has something that's like this. It's a method called finalize. And it's actually on the object class. It has this method called finalize. This is a method that is invoked when the object is garbage collected. That's not necessarily the same as when the object goes out of scope. It's when it's garbage collected. Objects can be garbage collected long after they go out of scope. They are ready for collection, but they may not be actually collected yet. So the finalize method is not usually something that you're doing anything with in Java. A destructor in C++ is a method. It has the same name as the class, so it looks similar to a constructor, but it has a tilde in front of it to say that it is the destructor. This is a method that gets invoked when you call delete on an object. So it's actually called as soon as you call delete on an object. It's not later sometime, it is exactly then. It's called when a stack allocated object goes out of scope, and not later, it's called exactly then. So it's different from Java's finalize in that sense. When you have a class hierarchy, the super destructor is called on the static type. So if we have a static type variable here, child pointer, a pointer to child C, and we assign that a new value that is a heap allocated or a dynamically allocated object of type child, when we call delete C, we're going to call the destructor on the static type and then its parent. So we have a relationship between child and parent. Child is a subclass of parent. When we delete child, a pointer to type child, it will call the destructor on this class, and then it will call the destructor on this class. So it bubbles up the hierarchy that we've got. This is unfortunately not constantly true, and we'll take a look at virtual destructors because this doesn't apply to things that have a static type that is higher up the hierarchy. So if I have parent star here instead of child star, it's not going to figure out that it needs to call child star's destructor first. So let's get rid of all this nonsense here. And what I want to do is really quickly take a look at trainer.h. This is one of the first ones that we built a destructor for. So that's right here. And when we added that, we added this as just a regular public method on this class. So we changed the class declaration to include that. And then in trainer.cpp, because we are taking ownership of these Pokemon pointers in this class, we're going to call the destructor on each of the Pokemon objects that we have a reference to in this class. The default destructor that gets created does not clean up those Pokemon pointers. So we have to go through this process of doing this explicitly ourselves. The other thing that I want to take a look at is this idea of a virtual destructor. So item here is this super type that we've got. We have to have a virtual destructor. This is an abstract class because it has a pure virtual method in it. So virtual and then equals 0. This makes the entire enclosing class abstract. We have to mark this as virtual so that subclasses of this can override this method, the destructor method for this. In item.cpp itself, we have an empty destructor. I've added a message here to print something out just to get a sense of where we are when destructors are being called. In potion.h, the actual subtype of this class, we have a destructor that's marked override to make sure that it actually does override the destructor in item.h. And then in potion.cpp, we also don't really do anything in the destructor other than to say that we're destructing this thing. So just a message to print that out. Yes? The reason that we want to override the parent destructor in this case is so that we can have, so this is not a good example because it doesn't do anything special in the child class, but if you had properties that you needed to release within the child class itself, because this is just a regular method, we need to make sure that it actually gets called when we call the destructor on a type. So I'm going to show this in just a second. If we go to test item.cpp here, when we call delete p, or if we call delete x, so if I do this, this is going to call the destructor on the subclass because the destructor on the parent type has been marked as a virtual method and it was overridden in the child class. So we have to mark it virtual so that we can override it in the subclass. Because in this case, it doesn't follow those rules of this, where it calls the child destructor and then parent, because the static type that we have for x here is a pointer to type item, so that it only knows about that class's destructor at compile time. That's right. Yeah. Yeah.
But if like in this case, the child class doesn't have any properties that need to be deleted, is it still necessary to make it virtual?
So it's a good practice to make your destructor virtual on an abstract class so that you can have destructors on the child class. In this case, the destructor on either of these classes doesn't really make sense because it doesn't have any dynamically allocated properties either in the child or the parent class. But generally, my advice would be if you have an abstract class, declare a virtual destructor so that you can do that in the child classes. Okay, so I'm going to run this just to get a sense of what all this looks like. I'm going to save it, and then I'm going to run it. So when I run test item here, I have this in subclass, in superclass. This output is coming from the constructor of those classes. And then when we call delete x here, the delete x is calling the destructor on this object x, but because it was marked as virtual in the parent class in item, we're calling potion's implementation of the destructor. So we're calling destructing potion first, and then it bubbles up to calling the destructor in item itself, so calling this destructor. And then it prints out the type of the thing that it's destructing here. So that's destructors. In a quick whirlwind tour, we did this last time we were here, but just trying to revisit it to get ourselves back on the same feet. Any questions about that? Yes, you need to implement destructors in the assignment. That person is wrong. For every class that you have dynamically allocated memory attached to it, yes. Okay. All right. So that's destructors. I do want to start talking about copy constructors, and I want to start talking about assignment operators. And because of that, I need to start talking about reference parameters. And because of that, I want to talk about ownership of pointers and ownership of objects. Objects, they've got a lifetime. So when you create an object, you call its constructor. Eventually, after you've done a bunch of stuff with that object, you either explicitly call the destructor or the destructor gets called on your behalf. The question that I have, or the question that I want to look at here is, who's responsible for destroying an object? So who is actually responsible for calling the destructor on something? Who is responsible for releasing the dynamically allocated memory that's used for that object? Generally, this answer is whoever needs that object last. whoever needs that object last is usually the same as the creator, the thing that created that object. So the thing that called new, or the thing that allocated that object on the stack, it's usually the same as that, but it's not necessarily the same as that. One of the decisions that we made when we started doing this Pokemon thing was in the trainer class, when we add a Pokemon to this trainer, so we're creating an instance of a Pokemon in our test trainer class, and then we call add Pokemon to this trainer, we're basically saying, let's give ownership of this Pokemon to the trainer object. So the main method in test trainer here is what is responsible for having had called the constructor for Pokemon. But the add Pokemon method that we're calling on the trainer is taking ownership of the Pokemon. The reason that we had a leak here was because in one case we didn't accept ownership of the Pokemon. We rejected the duplicate name of the Pokemon. But we've taken ownership of this object so that it's the trainer's responsibility and the trainer's destructor responsibility to release the resources that were acquired for that Pokemon type. The responsibility in general for destroying an object falls to the owner of the object. When we're thinking about dynamically allocated memory, I really want you to start thinking about who owns this memory, who is responsible for it, who actually has ownership of it, so that you know who should be calling delete on this thing and who should be calling new and who should be doing having those different responsibilities. Initially, the owner of an object is the enclosing scope. So in test trainer, initially the owner of the object that was Pokemon was the main function, the enclosing scope of this thing. So the main function had ownership of this thing, and then it was passed off to someone else. The ownership of an object can be transferred. This is just us basically saying, hey, I'm calling this method. Here's a pointer to some memory. It's your memory now. I'm not going to call delete on this. You have to call delete on it. Ownership of an object can be transferred, but also objects can be copied without having to transfer ownership in the first place. And this is ultimately what's going to get us to copy constructors, is that we can make duplicates of an object and then not have to worry about transferring ownership between things. And just always have a universal rule of whoever called new has the same responsibility to call delete. And we don't have to worry about ownership issues here. If you're interested in programming languages, Rust is a programming language that models this stuff as part of the language. So like you've got this concept of an object owner, and it's literally baked into the language that you're writing with and the compiler that you're working with. If you're interested in that, it might be worth checking out. Transferring ownership. This is basically what we did with the Pokemon class and the trainer class and the add item method. We've got a main method here that calls a constructor. It dynamically allocates an instance of this potion class. We call this method do stuff, and we pass it this instance of an item, and then we don't care about it anymore. We just say, I'm not going to do anything with this. It's the responsibility of the do stuff function or do stuff method to call the destructor for this thing. Basically, I'm just going to give up responsibility for this object. I don't really care what happens to it anymore. It's the responsibility of that function or method to delete it when it's finished. The problem with this is that we have to trust the thing that we're calling. We have to trust the thing that we're passing this to actually do something with that, and that it will release the resources when we're finished with it. With code that you have written, yourself, I don't know, like maybe you can trust yourself to delete the thing that you're passing ownership to. Like you wrote, well, I wrote both of these functions, but I trust myself. I trust myself most of the time to do this. Maybe, yeah, maybe. Code that somebody else wrote. So when you start to use libraries from other places or other parts of the standard library in C++, you can't even see the source code. You can't see the source code. You have no idea if the person that wrote that function or method is going to call the destructor on the object that you're passing to it. You have no idea. They might, maybe, but you don't know. You really cannot know. Because you can't trust somebody or yourself to call the destructor on an object that you're passing off when you're transferring ownership, it's not great. Sometimes you can't transfer ownership. So here is an example. And I actually want to go over to the Pokemon example. In this Pokemon example, one thing that I did when I initially set this up and before I distributed it to you was the example looked like this. So before I zipped up sample.zip and put it up on the course webpage, it looked like this. And it looked like this. So I'm taking a pointer to a Pokemon in this class, and I have passed it to my trainer here, and I'm basically saying, hey, here, you can have ownership of this object. The problem with that is that my trainer object in its destructor is trying to call delete on this object that I passed to it. Stack allocated objects, stack allocated classes, they're not dynamically allocated. They aren't dynamically allocated, they are part of the stack. So if you try to call the destructor explicitly with delete on an object that's part of the stack, you're going to get this. You're going to get a seg fault. And the seg fault that's happening here is a result of a double free. You're releasing you're trying to call delete on an object that's on the stack. And then when the stack frame gets popped off, when this method is finished, when this function is finished, when this object goes out of scope, the destructor is attempted to be called again. So you get this segmentation fault. So sometimes we can't transfer ownership of an object. The enclosing scope for this stack allocated object is what owns that stack allocated object. And you cannot give that object to somebody else to delete because it's not meant to be deleted. It just kind of goes out of scope and then the destructor is called. The solution is instead of assuming that or passing pointers around and saying, hey, this is your responsibility now, the solution is just don't transfer ownership in the first place. The solution is basically, instead of saying, hey, this is your problem now, I'm not going to call delete on this, instead of doing that, the idea is the thing that we're passing this object to should create a duplicate of it. It should copy its own thing into its own ownership. It should take ownership of a copy. That means that it creates this copy and you retain ownership. The enclosing scope retains ownership of the object that you dynamically allocated in the first place. And it's still your responsibility to destroy that thing, either by calling the destructor or letting it go out of scope for a stack allocated object. The copy object, this is now the responsibility of the thing that you're passing to. So you've given a thing to something, it's made a copy of it, and now it owns that copy. And yes, there are two copies of that same object now, but the ownership of those things is very clear. The copy that I made, I can call delete on safely and not have to worry about you calling delete on it too. So let's talk about copy constructors. This is quite funny to me, and it's meaningless, I assume, to all of you. Yes. How'd you figure that out? This is the wrap portion of the anti-pirating video. I believe this is like 20 minutes long. Yeah. I welcome you to search this up on YouTube. I'm pretty sure it's there. Not right now. No, not right now. This was a pretty big part of my childhood. Even though I didn't even get a computer in my house until I was in high school. And that's not because I'm so old that computers weren't around. It's because my parents were poor and we just didn't have a computer at home. And yet I still saw these ads when I was a little kid. Anyway, copy constructor. A copy constructor is a constructor, so it's part of our class definition. A copy constructor is a constructor that takes a reference object as an argument. Here is an object, and what you want to do in the copy constructor that you write is duplicate all of the properties from that thing. The default copy constructor, so there are default copy constructors that get created by the language. Default copy constructors will copy primitive types, primitive instance variables. It will do that on your behalf. They will not duplicate things that are pointed to. So if you have a pointer type inside of your class, the default copy constructor will not like do a deep copy. It's just a shallow copy. We can write our own copy constructors using the same sort of syntax that we used for the regular null constructor and then the other constructors that took arguments. The class name, 2 colons, the class name again. So it's a constructor. It has no return type. We've got a new keyword here, or a keyword that we're using in a different place, and we have a new symbol. This is a symbol that you have seen before in C. This is not the place you have seen that symbol before in C. This is not the place where you use this symbol in C. The ampersand here says, I would like to have a reference to this object. Not a pointer to the object, a reference to the object. The const here says, inside this method, for this object, I will not make changes to it. The object itself, I may call methods on it, I may read properties from it, but I will not make changes to it. I want to step through some stuff before we even start writing code for this. We're going to see how object references are different from pointers. They are not the same thing. They look similar, they are used similarly, but they are not the same thing. We're going to see using const. We're going to be using it on parameters to ensure that we, as coders writing this, are not going to make changes to the object that is being passed to us. And to tell our callers, the people or code that is calling our code, I promise that I will not make changes to the thing that you're passing to me. We're also going to use const on methods to indicate that this method does not make changes to its object. This is just an accessor. It doesn't make any changes to the data that's contained within the object itself. We're also going to look at converting pointers to references. And this is something you've seen before. This is dereferencing. This is taking a pointer to an object and kind of converting it back to its object by using that asterisk to dereference this thing. There are two types of ways that you can pass things to a method or things to a function. There's pass by value, which you've seen before. You've seen this in 1010, you saw this in 1020, you saw this in 2160, you saw this in everywhere. You've seen this everywhere. You've seen this idea of pass by value everywhere. There's pass by pointer, which you saw in 2160. You kind of implicitly saw it in Java in that when you are passing an object to something in Java, an instance of an object to something, it's a pass by reference. It's pass by reference. And when you took 2160, in this specific case, in this very specific case, your instructors lied to you. In this specific case, this is the thing I'm talking about very specifically today. I'm not talking about anything else in 2160. In this specific case, they said probably passing by pointer is kind of like passing by reference. And you all said, yeah, that sounds okay, that sounds right. I'm just going to use these arrows and like get on with my life and keep going. So there are two types of argument passing: pass by value, pass by pointer, and pass by reference. Here's pass by value. This is nothing new. This is stuff we've seen lots and lots of times before. I've got a main function. I've got a stack allocated variable here called number. I'm assigning a value to it that is 42. I'm passing the value to this function do stuff, and then I'm printing out value again here. And to nobody's surprise, even though I assign a value to this thing in my do stuff function here, I say value is equal to 20. In the main function, it still prints out 42. This is pass by value. In do stuff, this variable called value is a stack allocated variable. It's stack allocated. It is part of that method or function. And when we call this function, it is going to have a value copied into it. So when it's bound, when the value is bound to this variable, it's going to be a copy of the value that was passed to the function in the calling location. So here we change number gets, I don't know why I'm trying to explain this in like excruciating detail. Number gets resolved to 42. We copy 42 into value. Value gets printed out here. We change that stack allocated variable value to 20, but we're not making changes to the main function. We don't make any changes to that. Pass by value, great, good. We've seen this lots and lots and lots and lots and lots. Pass by pointer. This is what you started looking at in 2160. Here, I've got two objects. This is a C++ example. This is not a C example, but I've got a stack allocated variable in my main method, in my main function here called A01, and I'm passing 10 into this object. So in my constructor for object, I take this value, it gets copied into my, my variable, instance variable. I'm declaring another object, a pointer to an object, and I'm doing dynamic memory allocation. And I'm setting the value to 20. In the do stuff function, I'm taking as an argument a pointer to this object type. On this line, I'm saying I would like to pass the address of object 1, which is a stack allocated variable in my main function. I print out the value that it has. I change this object instance variable to be 30. And because this is a pointer, this is passed by reference in Java speak, Java parlance. When you're talking about Java, this is passed by reference. Because we're changing this instance variable, this actually has an effect on the object in the caller. I'm making changes to the object's instance variables itself. So when I print this out again, in the main function, it will print the value that I changed it to in that other function. It's a different scope, but because I'm using this indirection, the arrow symbol, I'm actually making changes to the instance variables in that class. Pass by pointer is pass by value. Pass by pointer is pass by value. They're the same thing. In this variable, or in this function called do stuff, obj is a stack allocated variable that has type pointer to object. It's a stack allocated variable that has pointer to object. When I call this function, I am passing a pointer to something, an address. The address is copied into this value, so it gets bound. The address of the thing that I'm passing is bound to that stack allocated variable. But when I do indirection here, when I use an arrow, it's dereferencing the pointer. This is the same as asterisk and then dot notation. It's dereferencing the pointer, and it's making changes to the actual memory where that object lives in memory. But it's still just pass by value. when I make an assignment to that variable that was passed here, that doesn't do anything in the caller, in the place where I'm calling this function. This is still just pass by value, but the value is a pointer. This is pass by reference in C++. I'm actually going to copy this code, and I'm going to run it in VS Code. I'm going to call this pbr.cpp. And I'm going to get the actual definition of my class here. I'm going to paste it in. I'm going to step through this. In the main function, we are still declaring two objects. On line 14, we've got a stack allocated variable. We're passing this value 10 into this object. So when we call the constructor of objects, the internal instance variable is set to 10. That's good. That's the same as it was before. On line 15, we're doing dynamic memory allocation, but it's still all basically the same here. I've got a pointer to my object. I'm passing 20 to this thing. When I call do stuff, the signature for do stuff has changed here. I'm no longer accepting a pointer to type object. I'm now accepting a reference to an object, that ampersand there. This is where we're kind of like moving the ampersand around to a different place where you didn't see it before in C. This is not where you'd put an ampersand in C. The ampersand here says, I would like to take a reference to an object, a reference to a thing of type object. Within the function, I use dot notation. I don't dereference this. I don't use arrows. I don't use asterisks here. I just use dot notation like it's a regular stack variable. I use dot notation. I make changes to the object's internal properties. And it actually has an effect in the same way that passing by pointer did. Line 10 here has an effect now. I'm making an assignment to this variable that's been passed as an argument to this function. And it actually has an effect. It changes the memory in the caller. So when I pass O1, O1 is a stack allocated variable. I just pass it without ampersand. I don't put ampersand here anymore. What I'm passing in this thing is an address, an actual physical address. I'm not passing a variable that has an address in it. That's what a pointer is. A pointer is a variable that has an address in it. I'm literally passing an address. So when I do dots, when I call methods on that address, the object that's at that address is what answers the message. When I put values into, or when I use values that are properties at that address, the object that I passed is what gets used. When I make an assignment to that address, the memory that's at that address is changed. A pointer is a variable that has an address in it. We are now literally passing the address so we can make changes to it. When I call this do stuff with a heap allocated variable, now I have to dereference it. This O2 is a variable that has an address of an object type in it. It's a small thing that has an address into the heap, and what gets pointed at by that address is a type object. To pass the address, or physically the thing that's there, I have to dereference that pointer. So I want to get the actual thing that's there. I'm going to make PBR here. I need to include stdio. Sorry, IO stream. I'm stuck in C here, sorry. I'm going to make PBR. I'm going to run PBR. And it's printing out numbers, but just quickly step through this again. In O1, we declare this object with 10 in it. O2, we're declaring it with 20. We're passing O1 to do stuff. Do stuff prints out the current value, which is 10. We make changes to it, we assign 30, and then we completely replace it with a new instance of this object that has a value 42. And when we get back to main here, we call getValue again, and the whole thing has changed. So now we're actually printing out 42 here. When we assigned to the reference, we're assigning to an actual address, and we're making changes to the memory at that address. The address of that variable is the same in both of these scopes. When we do the same thing with O2 here, we dereference it, we print out 20, we make a change to 30, we make a replacement object with 42, and then we get 42 printed out. Pass by reference is not the same thing as pass by pointer. Pass by pointer is a variable, a stack allocated variable that has an address in it. This is the actual address that's being passed around. Yes? So when I do this assignment, when I say obj is equal to object 42, we're basically taking this new instance of object that's being constructed here, and we're just like dumping it on top of what was there before. So the original object, yes, it's gone because we just reused the exact same memory that we did when we initialized it in the first place. Yeah. We're okay with this? It's a little weird. It's a little weird. It's a little weird and a little dangerous. It's a little dangerous because now we can actually make changes to the caller's objects. We could not do that before. We couldn't do that before. We can't do that in Java. We definitely can't do that in Java. When you're doing this, I've got this little note here. There's no new. We're not doing dynamic memory allocation here because we're just reusing the memory that's already there. We're not making new memory. We're just reusing the existing memory. Okay. Pass by reference is necessary because we need this for copy constructors. This is something that we have to put in the copy constructor. I don't usually want to do this. Like, this is really a strange thing for me to do, to take a reference to something and then reassign it. I can forbid myself from doing this by using the const keyword here. This says I will not make changes to this reference. So you're going to give me a reference. It's directly accessing the memory for this object that's being passed to me. But I promise I won't change it because the compiler will not let me change it. If I try to compile this again, make PBR, it's telling me immediately that I just can't do that stuff. I'm not allowed to do this because this class's object is, there's a bunch of stuff here about const. I'm not allowed to call anything that would change this object because I've marked it const in the argument. I can also do this on methods. So if I put on this get value, if I say const here, this is basically saying I will not make changes to my object that this method is being called on when you call this method. It's just a pure accessor. I'm just giving you something back, and no changes will be made to the object itself. So it still won't let me do that, which is good because I don't want it to let me do that. OK. And we did this, so good. So what I'd like to do now is we've got the syntax for what a copy constructor looks like. We've got this idea of references. I'd like to add a copy constructor to at least one of my classes before we end today. So let's go back to our example here, and I'm going to close pbr.cpp. This is in the slides, but I'll still include it in the sample that I give out at the end of class. I'm going to go to my Pokemon class. And the first thing that I want to do is declare this copy constructor so that I can actually call it. So to declare a copy constructor, I have to do something a little bit different than I had been doing before. To declare a copy constructor, what I need to do is say Pokemon, and then what I want to take as an argument in this is Pokemon ampersand, a reference to a Pokemon type. It has to be this signature for it to be a copy constructor. I'm going to put a semicolon there, and that's the declaration of our copy constructor, a constructor that takes a reference to an instance of this class. I'm going to go to Pokemon.cpp, and I'm going to declare and define this constructor. So the name of the class, the name of the constructor argument, and I'm actually going to go back to Pokemon, and I'm going to make this a const reference. I will not make changes to this object when it gets passed to me. I'm just going to copy stuff from it. In Pokemon.cpp, I need to have the same signature. So I want to have a const reference to this other object. And then I can treat this just like an argument that's being passed to this function. So you can use initializer syntax if you want to. So this colon, and then you can say things like what we've got just above here. You can say type, other.type. So you can use that same syntax, or you can say things like this arrow nickname is equal to nickname. All right, this is our copy constructor. This is a long-winded way to get to copy constructor. Copy constructor is basically making sure that when we call this object's constructor, we can pass an instance of an object to it. It will not duplicate that until we get into the copy constructor itself. And then we actually start making those copies. All right, I want to be respectful of your time. We're at the end of class. I don't want to jump into something new in the last 2 minutes of class, because that's never a good plan. It's never a good plan. What we're going to finish up next class is the copy constructor. I want to add a couple more copy constructors, but that's straightforward. And then I want to add assignment operators, which is also straightforward. Here's a quick preview of assignment operator. And the quick preview is this syntax is painfully ugly. It is painfully, painfully ugly. But we can step through each part of that. I'll stop highlighting it so that it's visible. It's really ugly. It's awful, but it's functional. It works. It does what we need it to do. So you should be able to describe and define this OCCF. You should be able to use destructors in C++. You should be able to use and describe reference types in C++. You should start being able to use copy constructors in C++. You can't do this yet in C++, but very soon after we start class on Thursday, you will be able to do this. Thank you all for coming out, and I will see you all on Thursday. Goodbye, everybody.